Our main goals in the growth from the Electrification Business Ecosystem project are developing and facilitating a battery technology business network and a cluster of expertise in Southwest Finland region and further in national and international level. Creating a regional competence center for battery technologies in Southwest Finland and strengthening the competitiveness of businesses in the region. Partners in this project are Yrityssalo and Turku Science Park. We will run this project until September 22, and our project is funded by European Regional Development Fund. And here is the project manager contact information. So my colleague Raimo Vuopionperä from Turku Science Park is another project manager. He's also present here today and will go through the questions you send in during the presentations. And if you want to know more about this project or want to cooperate with us, please be in contact with us. The purpose of webinar like this is to bring forward some information about the business potential in the electrification business. And here are some our working topics for next webinars that we have planned for the spring. For example, marine industry, new battery materials development, reuse and second life of batteries. And we would like to hear your ideas and comments about these and new ideas as well. So you can chat them in or call us or email us. And you can follow our project and the future events by subscribing to our newsletter. The instructions are here. But now let's get into this moment and into the smart use of batteries. That is the topic of today. And I will hand over to CEO Mika Kanninen from Akkurate. And he will tell us about the digitalization of battery diagnostics. So please, Mika, the stage is yours.
Thank you very much, Johanna. Very happy to be here, and thank you for having me here. So my name is Mika Kanninen, and I'm shortly starting to share my screen. Just a second, once you can see it. Okay, so first I would like to talk about what is diagnostics, battery diagnostics, in my opinion. Well, I have put it this way, that it's methods and procedures to understand or determine battery safety and performance, simply. And the traditional way of doing battery diagnostics is in the laboratory environment. And typically the purpose of this kind of a diagnostics is on the research, when new materials of the batteries are tested and trialed. It can be cathode, anode materials, separators or electrolytes, or then if not material research, then a real product development that some application needs a battery which needs to be evaluated. It can be used also for quality control measurements, taking samples from the production, and during the production start evaluating the batteries. And one is also that if there is some failures in the field or some unwanted performance in the field, then the laboratory testing can be used as a root cause analysis. And it's typically sample based. So you select a couple of tens of samples and evaluate the batteries, and based on that you try to estimate what is the performance in the larger population. And for these ones, physical battery testers, there are different type of testers, a lot of different type of testers available in the market, but they are physical and the batteries are connected physically to these testers. The advantage of having laboratory testing is obviously that the quality of the measurements and the quality of the data is very good. There is a high resolution and very detailed measurements can be done. And the test parameters can be programmed in advance and they can be changed the way you like. So it's very adjustable and the environment is very controlled. The concerns in that point is that there is a limited amount of samples, so you cannot test the whole population, and the equipments are pretty expensive. And it's not scalable in a way that it requires a lot of space. And it doesn't provide the understanding really how the field in the market, how the batteries are performing, because it's typically pre-testing or after testing. And then also one concern is the transportation of samples. There are a lot of limitations on that. Well, this is very shortly. Basically, each of the, at least most of the batteries are having that so-called battery management system. And it is taking into account and taking care of the battery, meaning that it's monitoring locally there, making the battery performing in balanced way, and then also protecting against faults. And it is integrated in the battery. Then when we talk about battery digitalization, I have interpreted it this way. So the batteries are connected. They are connected in the internet and they are in the field and operating in the market. And the way how to connect the battery to the internet, there are many ways, but the idea is that the BMS, the battery management system data that the battery management system is measuring, that is transferred to the cloud. And in addition to that one, typically kind of a digital configuration of the battery is created. Basically it's a piece of software that is kind of making the configuration exactly the same as the battery in the market. And in addition to that one, there are various ways of model the battery. There are simulation, how the battery behaves in different situations, and a lot of different type of models, physical models, and other empiric methods how to model the batteries. But nowadays also a lot of artificial intelligence and machine learning are used in order to create the models and in order to try to estimate the battery behavior. And the battery digitalization as such, what comes to the diagnostics of a battery, it is doing to the individual battery performance in the field. So you can select one battery to see how it's performing in the field through the internet, so remotely. And it can be also be for the checking how the battery is behaving there. And then you can compare different individual batteries to each other. And the diagnostics can detect anomalies and different trends. Then another word in addition to diagnostics is a prognostics, which is basically a diagnostics, but it is trying to estimate the behavior in the future. And typically these estimates are used for estimating the remaining life of a battery. What is the residual value of the battery, and how the batteries are becoming end of life, and it can be used for planning the material flows, for example, to the recycling, or to second life use. And the benefits of having battery digitalization or remote diagnostics and prognosis for the batteries is that it can basically cover the whole population in the market. And it is enabling a lot of cost savings in terms of preventive maintenances, for instance, or making the adjustments for the battery usage in order to get it last longer. It is also enabling a lot of more statistics, how different, for instance, certain battery lots are behaving in the market. If there are certain countries where the batteries are not used the same way as in some other countries, and so forth. There are numerous ways of enabling statistics for the batteries. And it's also enabling new businesses. One good example is renting the battery or battery as a service. So instead of selling the battery, the manufacturer or some other provider can actually rent the battery. And having the data from the field is very much supporting that kind of business models. And yes, it can be done remotely, so no need to go locally there and measure the battery. Basically, you can get remotely each of the batteries that are connected in the internet. You're gonna have the diagnostics. It is very scalable, as no physical equipment's needed, and it is supporting the circular economy, as I mentioned, on the material flows. And also it supports different players in the value chain, meaning the, for instance, battery manufacturers, integrators, the users of the batteries or operators of the batteries, but then also the recycling companies and the second life companies. The concerns of this approach is data quality. So obviously it is not as good quality data as in the laboratory. There are measurement errors, there are no data points, meaning that sometimes there are interruptions on the data. The amount of data, it can be either too little or in some applications it is huge, enormous amount of data, and how to handle that amount of data, that's a key point. And sometimes also availability of the data. So for instance, in a big battery, which is for instance, for the energy storage, for energy production, it can be megawatts of size of a battery. And sometimes the availability of the data is only certain level, meaning that you can measure maybe the total battery or then just pick parts of the battery, but you cannot get data from the cell level. And that is one. Also, some connectivity issues, especially in the e-mobility area, that the amount of data is too big, or then there is no connection available yet.
You have 4 minutes left.
All right, that's perfect, because now we can look at a little bit what Akkurate is doing, which I'm representing. We do have both ones. So we do have the testing laboratory. We can do the sample-based testing, but our future view is that it all goes digital, meaning that the batteries will be connected to the internet, and that's the kind of a future. And we have a ready-made solution for that one. We have a battery diagnostics platform or prognosis platform as well. So it's a software that is analyzing the data that is coming from the field, from the batteries. And we have created these digital models for the batteries and different algorithms to automatically detect if there are anything wrong with the battery or the usage of the battery. And we can provide our kind of analysis and diagnostics and prognosis to our own UI, which is a web-based application, or then another solution is that the results and our analytics are integrated into customers' own system through APIs, and that is basically already available, and happy to discuss with any of you if you have an applications and interest to have a word. Please contact me or then my colleagues Lauri or Mikko, and we are happy to talk more. Thank you very much.
Thank you, Mika. There does not seem to be any questions, but I have this layman question. Have you estimated how much in average you can make the battery life longer with your solution?
Well, we do have some calculations on that. Obviously it is very much depending on the application. For instance, in the passenger electric vehicles, it's pretty difficult because anyway the end user is the one who is using the battery. For instance, for the stationary energy storages, it can be significant difference. It can be up to 2 years differences based on how you use the battery. And it doesn't even have to be very radical change.
Oh, that is quite impressive, in my opinion. Now there's other question. Just a minute. What is your view on the battery passport concept, and how does those plans relate to the Akkurate solution?
Yeah, that's a pretty good question, because there has been a lot of discussion in EU and globally as well. The tracking of the battery from the mine to the grave, and we do very much support that idea. And as our system is well, it's a software platform basically, and it can be connected to APIs, so we can take from battery vendor or even from the material vendor the traceability information, and we can input that into our. We can identify each battery separately or even up to each cell in the system, and every of those has an individual code basically, and therefore we can use the traceability data from the vendors, and we can contain that in our system, and then we can use that data for our estimations and information that we are providing to our customers. So definitely we are supporting that, and our system is capable of having that feature.
So since Johan had some problems with her connection, does anyone in the audience have still more questions? I do have one question or kind of comment that how readily the data is available from different manufacturers, because usually they are kind of jealous of what the data is there, and what is the granularity of the data you get from the manufacturers?
It depends, and you are right that some of the manufacturers are kind of jealous about the data, but so far at least we have had quite good success on having the data, and there are different ways of how to handle the data. For instance, we can just connect to the cloud of a supplier so that we don't really get the raw data into our own servers. Thus, we don't save the raw data as such, but we just kind of borrow the data and use the data.
Okay, just kind of continuing questions that sometimes the data you get from the manufacturers is actually on the battery level, not on a cell level. Does that pose a problem?
Well, obviously it's impacting on how detailed analytics you can provide, and in this case, obviously we are not able to provide cell level analytics, and our approach is that whatever the data level is, we can do analytics. But the benefits, what the customer can get, depends on how detailed data we can gain.
Okay, I think we can all thank you, Mika, for your nice presentation. I don't know whether Johanna is back on the line, but let's start moving towards next presentation, who is by Pentti Bruun from L7 Tribe. Pentti, do you have your slides on ready?
Yes.
Okay, go ahead.
And you can see it.
Yeah, since I don't have the introductory slides from Johanna, so go ahead. Thank you.
Okay. Hey, first I would like to thank Yritysalo for organizing this event and offering the possibility to introduce L7 Tribe to you. So my name is Pentti Bruun. I'm the CEO and one of the co-founders in L7 Tribe. In this presentation, I will cover those 4 topics. Very short introduction of L7 Tribe, then L7 Tribe technology in a nutshell, smart energy subsystems, what we have done so far in Luxturin 5G in telecom sector, and other use cases, what we have done already or what is ongoing. When establishing the company almost 10 years ago, our target was to build a full electric L7 class vehicle for inner city logistics. That's why the name is L7 Tribe. My responsibility was fundraising, and I have said many times that thank God I didn't succeed. So we have to focus more deeply, and we decided to concentrate to powertrain technology instead of the whole vehicle. Now, I think our statement is very clear. Everything we do, we believe in challenging the status quo of battery solution. We believe in thinking differently. The way we challenge the current players is to make products that use batteries connected in parallel, not connected in series as our competitors do. Our products ensure long lifespan, lower total costs without balancing problems. So we have faced those 3 biggest issues in the markets: reliability, costs, and connectivity. For example, in light electric vehicles, up to 70% of the overall vehicle costs are coming from powertrain. Those first 2, reliability and costs, are tied very closely together. But in many cases, use cases, real-time connectivity is needed to satisfy customer needs. And also what Mika said earlier, it's very important to have data, raw data from batteries as well. So how we have solved these problems? We have a long and strong lithium battery and power electronic background. My background is coming from investment banking and VC, but my team has very good knowledge about battery technology. So everything what we are doing is based on our patented technology, how to use batteries more efficiently and give the longest possible lifespan to the most expensive part of many solutions, batteries. Our core is the technology what we are using when raising up the voltage from parallel connected batteries. As I mentioned earlier, all competitors are using series connected batteries. And when using parallel connections, we don't have unbalancing problems. We don't need any extra battery management systems. To offer proper solution for customer, we have developed a smart energy backup solution which includes parallel connected battery pack, DC-DC converter, hardware and software for controlling and monitoring energy usage in different applications. In these slides, you can see those two connectivity devices, CAN gateway and pole controller. They are almost the same. CAN gateway uses cellular connectivity and pole controller is using Ethernet. So referring what Mika said earlier about battery diagnostics, our communicate devices can offer the raw material, raw data for more accurate analysis. Our three most important value props are here. We can give longer lifespan for the battery pack, and that's how it lowers the overall costs as well. It offers real-time connectivity and give a high security, easy to use cloud system as well. Now we can jump to our customer case, what we have done. So a few words about Luxturim 5G. It's a Nokia-driven innovation ecosystem developing and demonstrating fast 5G network based on smart poles with integrated antennas, base stations, sensors, displays, and other devices. One of the key challenges driven this project is the climate change. Climate change and urbanization set a lot of pressure on cities. Already now, more than 70% of the global energy consumption and carbon emissions originate from cities. If I think this statement from our point of view is very important for us, because our role in this project was in the first hand to develop reliable energy subsystem. But during the project, we developed also a new way how to give a secondary purpose for the batteries instead of only waiting for grid power outage. Now I would like to show you a short video. You can see what we have done here. Let's check.
I guess the voice is not hearing, or do you have a voice?
There is a voice, but sorry, I don't know how to put the voice on, but there is a text. I think you can see all what is said here in video. Okay, sorry. And now I think you all understand in Luxturm case, it's very crucial to have real-time data from the batteries, and that is what we have solved in this case. Okay, other use cases. We have built powertrain devices for few power categories and use cases. 250 watts solution is for LAVs, for electric bicycles, kickscooters, e-forklifts, and small energy backup systems. The second one, 600 watt solution, that is what is used in 5G nanostations. 2 kilowatt version is for e-scooters and small rickshaws, three-wheelers. And in our R&D roadmap, we have started planning already for higher power solutions up to 10 kilowatt solutions. So there is a lot of different use cases where this technology could be employed. But as a small company, we have to focus somewhere. And what we have done, we have decided that our main focus areas at the moment is those three market segments: telecom, LAV, and automotive. In telecom sector, the same what we have done already in 5G nanostations will be developed to the higher energy, bigger energy subsystems for 4G macrostations as well. There is one project, commercial project ongoing at the moment. For LAV, we have developed the whole powertrain excluding motor for one electric bicycle manufacturer, and the negotiations are ongoing with another solutions as well. And in automotive industry, we have been selected for tier 1 company for one German EV manufacturer. They will use our connectivity device in their newest e-car, which is coming to the market after 12 months period. We have other pilots ongoing with the same CAN gateway device as well. If you want to see more deeply our devices, specifications, you can find them in our web pages. Thank you very much. I'm happy to answer your questions or if you have any comments.
Thank you, Pentti, very much for your presentation. There is indeed time for 1 or 2 questions, so you can send them in to the comment section. And sorry, I had some technical problems earlier. Thank you, Raimo, for going on with this webinar.
Before anyone types in anything, I just have a kind of questions. What is the range of you if you're losing cells? How much you can cope with that your DC-DC conversion still works? You actually losing 1 or 2 cells or even more from your pack. Of course, depends on the pack size, but
it depends on pack size. But if you think that all are connected parallel, and if you lose 1 or 2 cells, or we can name how many, we have still the 3.7, 3.6, something like that, where we start to raise the voltage up to the motor or radio usage. So it doesn't matter if there is bad cells inside the battery pack.
Okay, it's mostly related that at some point of time you start having problems that you are consuming too much energy from certain cells. DC, yeah, certainly that works, but you might have heating problems or something like that because the power still must come.
Yeah, we have had few studies in Aalto University, and we haven't seen any thermal issues. So I don't know how technically that has been solved, but what I have heard from my team that we don't have any thermal issues at all in these cases, what we have done.
Okay, then does anyone have a questions or I can have one kind of comment. I'm kind of wondering why everyone else is using this serial connection, because it is from my point of view the parallel connection is the way to go, and you have just a different DC-DC to reach the required voltage levels. And by building batteries like this, you actually might avoid some problems with you have a high voltage of serial connected batteries. But this is just my personal view. Any comments?
Well, I would say that for our part of it, from Carditech, we cannot use only parallel connection, as we work in 1000-volt range and 1000 amps. So we need the mixture of both. We need a lot of series connections combined with a lot of parallel connections. But L7 Drive and especially Daniel Salonen have been very helpful and very ingenuitive on this part of helping us in succeeding our battery project.
Thank you, John, for your nice comments.
You're welcome. But this is the fact.
Okay, thank you. Thank you for your presentation, and thanks for the active comments. I'm afraid we have to move on to our last brilliant case. That will be training AI for energy storage applications, considerations of data quality, and CEO Jukka Anttonen from Unified Chargers will be telling us about that. So please, Jukka, floor is yours.
Yeah, I guess you can see my screen now.
Yes.
So, hello everybody. I'm Jukka Anttonen, and I'm CEO of Unified Chargers. Also, I bear some CTO role in the company. A little bit about us. We are a Finnish fast charging technology manufacturer, and also we are developing our own technology, and we have just I would call it that we have just entered the market and have sold a couple of our compact DC fast chargers. And most of my topic today will be about the data quality, not much of an application. Of course, I will talk about a little bit in the end. But mostly I'm preaching here that you guys continue doing your good work, because we are going to need it in the future. So, how to train an AI? 4-step program, very easy. First, you just need some sort of data set where to start from. Then you validate your data. Is it any good? And put it in your AI and test. Does it perform as you expect, or does it look a little bit like the real world things that you see on your own? And in case not, repeat. And do this process over and over and over again. And computers are very, very effective doing that. But there are some things that should be considered. Like I mentioned, computers are very, very capable of doing well-defined tasks. But this raises up a couple of issues. First of all, somebody has to define the task, and somebody has to be in top of things and know where we are going with this thing. And currently, the issue is that the computers cannot define these tasks themselves. We have to do it for them. And how we do these things is like we use some sort of data sets where we start this process. And there are a couple of ways of approaching this. Mostly today we have seen these statistical methods, but there's also like a purely iterational methods. And in the real life, it will be a combination of these both, how these things are done. And basically, you can think an AI to be like a very powerful statistics tool. And for the training process of you have the data, but in some cases, like here, this is old news already, but it's a very good example of how to perform when you have well-defined tasks. This is a Google AlphaZero chess player. So basically, in a way, we can say that there's no initial data set. In this case, they didn't use any statistical models or known good strategies in chess, anything. They just made two of these AIs play against each other, and that's it. And learn from that. So I would call this like a pure iterative process. How they have achieved this. Okay. In most cases, in energy storage systems, this approach really cannot be fully utilized. The problem on the energy storage systems is that what state our energy storage should be at any given time, so that we get the best performance out, the best profit from the markets, for example, in this case, and whatever you are trying to achieve with this. So you can utilize some historical data, for example, energy usage data from the grid. You can see patterns from there, how they are performing, and use that sort of thing. Also, the data can be simulated so that it's not real, but to see how the system performs in the new type of scenarios, and how the energy balance can be achieved. And when we go into this kind of approach, we need the data quality assessments, because it depends a lot what kind of data you have. We have had good discussions today about the raw data and a little bit of the quality of it. So that, for example, laboratory, you can have very high quality data points, but the problem is you can have them only so much. And from the field, you have much more measurement points, but you probably don't have very accurate equipment there compared to the laboratory, for example. And that's where we use all sorts of scientific and statistical evaluating systems. Is the data correct? Is it good enough for us to work with? And classic issues with the poor data quality. The most common one is lack of data over the whole area, so to speak, or it's a similar issue with if the data points are too similar with each other. So this leads the system easily to self iteration. Let's look at that a little further. But it means in shortly that even though the system is based on statistics, wrong weighing can cause it to think that the situation we are in is like abnormal, or abnormal compared to the reality. Okay, other things are like the data points are given too high or low weight based on age, on source, or whatever, and this has the same kind of reaction what can happen. And of course there can be noise in the data, like misread values, for example. This may lead like overacting or underreacting on the situation at hand, and then of course we can these days we can run up to too much data. The system is overloaded and it cannot perform its tasks fast enough or in real time. Preferably we would like to have it in real time. Okay, and the also couple of two classics. Dataset doesn't represent the phenomena you are actually trying to investigate, and correlation is not necessarily causation. So I have one example here on that when the data points are too similar with each other. For example, energy storage system. In most use cases, you don't want your battery to be completely depleted, and for the battery life, you really don't want it to be fully charged. So typical use happens between 30 to 80% state of charge most of the time. So that area is very well covered, usually in data over time. So there's a lot of data points on that. So it might turn out that the system starts self-iterating itself, meaning that it's starting to see like a false battery degradation, even though the battery isn't going bad at all. So it means that the system starts thinking that the 80%, which is basically the maximum you are charging your battery, is the new 100% on the system, and vice versa. The same, the 30% on the low end state of charge, the system starts thinking that it's the new 0%. So a large portion of the battery might get unused, and it might be interpreted to be that the battery is getting old or defected. One very small scale example on this. This is a graph of my laptop battery, how it's performing based on its own internal statistical methods that it's using. So here we have the same issue. I rarely use all of my laptop battery, and as we can see, this solution thinks it's 100% accurate from 50 to 80% state of charges. Out of that, well, it's an honest AI. It tells that it has no idea what's going to happen if we go outside of this range. Okay, I have cheated a bit on this. I have set a hardware limit on my battery so that it doesn't charge more than up to 80% at any situation. So basically, this system is missing all the data points above 80%, and well, because rarely I run out of battery, it's also missing all the data points on there. So the solution in this case would be just to add more data points, come up with them, and have a better weighing on the data points. And also in this particular case, it would be useful for the system to be accessing the system parameters, meaning that there's a underlying cause for this, but the system doesn't know it. It's like that all the information isn't transferred into the models for various reasons. It can be like a human error, that somebody just don't think that this is necessary information, or somebody makes changes to the system without the analyzing system knowing that it's there's a system change. So it may lead erratic behavior. So a couple of disclaimers. Both of these examples are way out of proportions and out of context here. So generally, these issues are very well taken care of in all these applications, and it's always good to keep in mind what is the problem that we are solving with this data set that we have. Does it represent it properly? And when you can define your problem very well, the outcome is usually also better in that case. So what this has to do with EV charging? Well, EVs are basically energy storages on wheels, mostly untapped resource these days, and I would call this almost a low-hanging fruit here. It would be very beneficial for our energy system and electricity grid if we can use these batteries. Let's call it wisely, and it could be simple as we hear a lot of talking about V2G, meaning vehicle to grid, so that the car would be pumping energy back to the energy grid, but we haven't finished yet doing the first stage of what we call V1G, meaning that we would just control the energy flow into the battery and the car wouldn't feed back at all. So we can use this to stabilize our energy production and have it on more stable level, which means that our energy systems can run on higher efficiency, and that will lead to less emissions in energy production, and what we are currently missing in our systems, which I would like to have very soon, is the user input on these systems. All the things that we have discussed today doesn't really involve the end user at all. These are stationary systems, and there are trained professionals using these equipments, and but we have also, so to speak, running around a large battery capacity in our grid, and it's connecting it randomly. So what if we would add like a new functionality, maybe to the car or something like that, and ask user, when do you think when you're going to unblock your car next time? So with that sort of new information put into the system would be very beneficial to predicting what's going to happen, because we all know that predicting future is really hard, and but sometimes it's very, very helpful to ask somebody who knows what they are going to do next. And how this comes into our products is that well, we are rolling out this and doing testing on our own with this ask user what they want when they charge their car. So basically, currently we are giving them two options. First, do you want to charge your car immediately, or do you want to charge your car cheaply? So we bring some incentives for the end user to give us the information that when they expect them to leave. The downside for the user is that if they give false information, it might be that the car doesn't get charged as much as it would normally, depending on the energy situation on the grid, for example. Any questions?
Thank you, Jukka. How willing do you think will the users be giving the information?
Mostly we see that there are even the small incentive makes people to give this information, and we see that it's not that personal or invasive information. It's an estimate of what the user will provide, and there is a risk for the user if they give false information. For example, the car might not be fully charged in the morning when they leave. Okay, that's one downside. But they also have the option to use it immediately. So then we have to adapt, like in real time, what's going to happen. So if we know that we are going to overload the circuitry or something, so we have to limit the charging anyway. But if we are given the information that when the user is approximately leaving from the user itself, it gives us a lot of room to play when to charge the car. Of course, these things can be done statistically. We know that most of the people are leaving in the morning. They are plugging the car in at the work an hour after they are leaving, roughly at 4 o'clock, and these sort of things. But and these will help. These are very helpful information already, but the detailed part where you can do the rest of this, you can achieve basically half of it. You can achieve just by looking statistic models, but to achieving the rest of the half, you have to ask the user what they are.
Okay, thank you.
Hopefully this answered your question.
Yes, really profoundly. Yes, thank you. There's still room for one short question. We have 1 minute time left. If there's at least one comment. John Yeteman says, Jukka has delivered fast and fact-based answers to all our questions during our entire project. He is our charging supplier, and we will continue that position. So that kind of feedback to you, Jukka.
Thank you, John.
Okay. If there are not any questions, I thank you, Jukka and Mika and Pentti, for interesting presentations today. I think there is lots of know-how about the smart use of batteries, but it seems that there's still room to apply it even more in the future. And thank you for active participation to you all listeners. As promised, this recording will be sent to you in near future, and all the presenters have promised to share their presentations too. And thank you, Raimo, for co-hosting and being an active questioner here. And thank you, Lauri, also for helping me out with technical details. And please be in contact with us and subscribe to our newsletter and follow our future events. Do you want to say something, Raimo?
No, I just typed already in the discussion that expect the next webinar to happen in just before the Southern Finland part of the winter vacations. So tentatively 17th of February we are going to have a next webinar. So advertise that to people around you. So the topic probably will be around the marine sector of usage of batteries, but that can still change. So, but please send us also suggestions what kind of topics you would like to hear, because we can we are harvesting the whole company and university potential in southwestern Finland.
Yes.
So thank you.
Yes. Thank you, and have a nice rest of the week. Bye-bye.
Thank you. Bye-bye.